In this video, we're going to go over the AP Calculus AB 2018 exam free response question number 4. So in this question, we're given this table where we have t measured in years, h of t in meters, and this is modeling the height of a tree. Important that they say that h is twice differentiable. That'll be important as we go through here. So question A says use the data to approximate h prime of 6. Now we know that h prime of 6 is the derivative of h at 6, or the instantaneous rate of change at 6, the slope of the tangent line at 6. But we are estimating that value. So when we estimate an instantaneous rate of change, we use an average rate of change. So that's just slope. And we have this table where we've got t is 2, 3, 5, 7, and 10. And we can estimate h prime of 6 by just finding the slope between any 2 points on this table that include 6 within the interval. It would sort of be unreasonable to say that the best estimate you can come up with is the slope from 2 to 3. Like, that just doesn't make any sense. The most logical one is from 5 to 7. But as long as you include the 6 within your interval there, you're going to be okay. But I'm going to do the 5 to 7 slope because that just makes the most sense. That's the best estimate that I can get here. It's the smallest interval that includes t equals 6. So it's just slope. So that's going to be 11. So for part A here, it's 11 minus 6, my two y values, over 7 minus 5. My two t values in this case. And if I simplify that, I'm going to get 5 over 2. I don't need to simplify it, but I will here. And that's going to be meters per year, because they want units. Meters per year. And then it says to interpret that. Well, that's, and it says to interpret h prime of 6. Not our estimation of h prime of 6. So just interpret what h prime of 6 would mean. And so that means h prime of 6 is the instantaneous rate of change of the height of the tree, running out of room here, but the height of the tree when t equals 6. It's important that we have that when t equals 6. We've already said that it's instantaneous, but we want to make sure we're clear that this is the instant we're talking about. That's always important to have when you're interpreting any sort of derivative, is the time that it happens at. All right, part B, explain why there must be at least one time t on the interval from 2 to 10 such that h prime of t equals 2. Now this is a classic setup for the mean value theorem. Why does there have to be a time where the instantaneous rate of change equals 2? Well, we know from the mean value theorem that as long as we're differentiable, then the derivative has to equal the average rate of change at some point within the interval. So the default here to go for, it doesn't always work out, but the default is to actually just find the slope from 2 to 10 and hope that that slope actually equals 2, because then by the mean value theorem, because h is differentiable, there must be at least one point where the instantaneous rate of change equals the average rate of change. So we'll go ahead and just try that interval that they give me, and you might already be able to see what's going to happen, but just to show that we should actually try it. So if we do from 2 to 10, I've got a y of 15 and a y of 1.5 over a t of 10 and a t of 2. when I simplify that, I mean, just a little bit here, 15 minus 1.5 is 13.5, and 10 minus 2 is 8, and 13.5 divided by 8 is certainly not 2. So that didn't actually come out the way that I hoped it would. But we'll just check a few others here and see, what can we get here. And if you just look at it, you're saying, okay, I need the slope to be 2. Well, if you look at these two, that's a difference of 4 in the y values and a difference of 2 in the t values. So if I take the ratio of those, I'm going to get 2 as my answer. So that's the one that I want. So sort of, okay, this didn't work, but 6 minus 2 over 5 minus 3 does in fact equal 2. And so then we can say, so, because it wants us to explain, so by the mean value theorem, which you're allowed to abbreviate as MVT, since h of t is differentiable, must say that, differentiable, sorry I ran out of room, but that says differentiable. Since h of t is differentiable, there must be at least one t value on 2 less than t less than, 3 less than t less than 5, such that h prime of t equals 2. And we've already shown the work here for why we chose the interval 3 to 5 rather than 2 to 10. So that's part A and B. I'm going to clear some of this out of the way so that I have more room to write and we can still see the question here. Okay, so we'll get rid of our part A. Don't want you. Don't want you. Get rid of all my part B here. All right, in part C, wants us to use a trapezoidal sum. Always have to be careful with our trapezoidal sums. To approximate the average height of the tree over the time interval from 2 to 10. And so we need to, in this case, use the average value function, where the average of f on the interval from a to b for some function f is equal to 1 over b minus a times the definite integral from a to b of f of x dx. And so in this case, they're just asking us to approximate this definite integral value using a trapezoidal sum. But we still need this thing here. So since we're talking about from 2 to 10, we just have 1 over 8 and then times my trapezoidal sum. And on an FRQ, I'm pretty much never going to simplify my trapezoidal sum. I'm just going to think about each individual trapezoid. So I've got one trapezoid here where I always have 1/2, and then base 1 is going to be 1.5, and then base 2 is going to be 2. So 1.5 plus 2, and then the height of this trapezoid is the length of this interval here. So from 2 to 3 is 1. Then I add the next trapezoid, 1/2. Now base 1 becomes 2. So now this is now base 1, and this is base 2. Plus 6, and now my height is 2. Plus, keep going, 1/2. Now this is base 1, this is base 2. 6 plus 11. Now my height is again, okay, from 5 to 7, that's 2 again. Then plus 1/2 times base 1, which is now 11, plus base 2, which is now 15, times my height is now 3. And I would just leave it like that. No need to simplify all that. Even if you had a calculator on this one, I wouldn't simplify. All that's going to happen is you're going to make a small mistake and lose a point. Just leave it like this and you're good. Okay, so that's part C. Once again, I'm going to clear that out of the way because I think I need a little bit of room here to walk through part D. All right, so in part D, they want the height of the tree, or they give us this new function that models the height of the tree. You know, before everything up to this point, we're using h to model the height of tree. Now they're giving us this new function g, where the input here is, instead of years, the diameter of the base of the tree. And so what they want us to answer here, you know, there's a lot of writing in this part, but they're asking, what is the rate of change of the height of the tree with respect to time in meters per year at the time when the tree is 50 meters tall? So the first thing to think about is, okay, well, just, all right, they want the rate of change of the height of the tree with respect to time. So what they're looking for there, since g gives the height of the tree, they're looking for dg, but not dx dt, because x here is the diameter of the base, whereas t here is time. So we're looking for dg dt when g equals 50. So when g equals 50, which is strange because usually we're thinking, okay, take the derivative, plug in a number, just like we did up in part A, just plug in 6 as t because this is already h of t, but now we're not plugging in t. Also, the function isn't even in terms of t. So this is really a chain rule problem, a related rates problem, if you will. dg dt is going to be dg dx, which is just the derivative of g, times dx dt. Because just simple fractions, these dx's cancel out and I'll get dg dt. So dg dx, again, that's just g prime. This is g prime of x. We could write it that way. And then dx dt is given to us that at this particular time that I care about, when the tree is 50 meters tall, the diameter of the base is increasing at a rate of 0.03 meters per year. So x represents the diameter of the base, and it's changing at 0.03 meters per year. So I can just drop that right in there. And then I just need to figure out what's g prime. And that's a little ugly because it's quotient rule, but I can do it. G prime of x, you know, if you need to sing a song, low 1 plus x, d high 100 minus high 100x, d low, which is just 1, square the bottom, and away we go. So then I just need to plug in x, but what am I going to plug in for x? Because what we want this derivative when the tree is 50 meters tall, but 50 is g, and I need to plug in x, the diameter. But we have this function, g of x equals 100x over 1 plus x, and g of x is the height, and the height we're given as 50. So I set g of x equal to 50, and then I solve for x. Solve that for x, and you get 1 for x. Take that, plug it in here, figure out g prime of 1. And if you simplify that to once you get that g prime of 1, I believe you get 25. And then you just take that answer, change colors here, we're getting a little bit messy. Take whatever you get here, which I believe is 25, and plug it in here and then multiply by 0.03. But, we know we don't need to simplify, so really you could just take this g prime of x and replace every x with a 1, and then take that whole expression and plug it in down here, and then just leave it as that big ol' ugly thing times 0.03. Now I would clean it up a little bit. I wouldn't write the 1 over that like I have here. I want the AP readers to be able to read what I'm writing, but I'm constantly battling my stylus here. So that's number 4 from 2018.